Hello everyone, welcome back to the channel. Tonight we drift into the quiet world of hibernation, a place where life slows almost to a stop. Beneath snow and soil, within bark and stone, harps grow quiet, and the earth holds its breath. The world seems frozen in silence, yet beneath that calm, life continues in secret. Hibernation is nature's hidden art of survival. It is the science of waiting, conserving, and trusting that warmth will return. Frogs freeze solid but return to life. Bears sleep for months without food or water, and tiny mammals that their hearts come to an almost total standstill. Scientists now search for ways to bring this power into our own lives. Hibernation, like protect astronauts, preserve organs, or slow the rhythm of aging itself. What began as a winter strategy may hold the key to our future. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way. Here too, one sleepy soul at a time, but for now, just breathe. Allow your eyes to grow heavy and let the hush of winter cradle your thoughts. Let's begin. Frogs can freeze solid and come back to life with the spring thaw. When the cold arrives, the wood frog performs one of nature's most astonishing transformations. As ice begins to spread through its body, its heart stops completely. Breathing ceases, blood freezes, and every visible sign of life disappears. But moments before this happens, the frog's liver floods its bloodstream with glucose and urea, saturating every cell. This mixture acts like a biological antifreeze, keeping delicate tissues from being torn apart by forming ice for the entire winter. The frog remains frozen stiff, its cells locked in suspended animation. When the temperature finally rises, the ice within its body melts in careful order. The heart begins to pulse, the lungs draw breath, and within hours the frog hops away as if nothing happened. No machine can yet copy this perfect pause between life and death. It is living biology mastering the art of controlled freezing. Hibernation slows aging by reducing cellular damage over time. Every heartbeat, every chemical reaction in a living cell leaves a trace of wear. Oxygen keeps us alive, but also creates unstable molecules that damage DNA, proteins, and membranes. In hibernation, metabolism slows so dramatically that this internal weather almost stops. Cells shift from production to repair, using energy not to build but to mend. Waste removal improves, oxidation drops, and proteins last longer before they must be replaced. Even the brain, resting in deep torpor, clears away accumulated toxins more efficiently than during normal sleep. Studies show that animals that hibernate often live significantly longer than similar species that stay active all year. Their bodies age in slow motion, protected by the chemistry of stillness. Each season of rest becomes a quiet renewal, proving that sometimes the best way to survive time is simply to let it pass more slowly. Bears hibernate for months, yet wake with muscles fully intact. While humans confined to bed lose strength rapidly, bears manage to stay still for up to half a year without wasting away. Inside the den, heart rate drops to a handful of beats per minute, and breathing slows almost to nothing. Yet the bear's muscles stay dense and strong. Its body recycles nitrogen from waste and converts it into new protein, feeding muscle fibers even without food. Hormones maintain bone density, preventing brittleness that would plague any other mammal in such stillness. Low-level tremors in the limbs keep circulation active enough to nourish every cell. When spring sunlight filters through the den, the bear rises immediately, walking with full strength as if it had never slept. Researchers hope to one day adapt this natural miracle to human medicine, allowing patients to recover from long immobilization without losing the very strength that keeps them alive. Bats slow their heartbeat from hundreds per minute to almost none. A bat's metabolism is designed for extremes. In flight, its heart can beat faster than any mammal its size, pumping hundreds of times per minute. But when winter arrives and insects vanish, it enters torpor so deep that its heart may pause for minutes at a time. Blood flow nearly stops. Temperature drops to match the cave around it, and oxygen use falls to a fraction of normal. The bat becomes a small living ember of energy, burning just enough to endure. Periodically, it stirs, raises its temperature, checks the air before slipping back into stillness. The control is absolute. balancing on the edge between life and death. By surviving months in this state, bats conserve enough energy to outlast famine. Their bodies show that endurance is not always about speed or strength, but about knowing exactly when to be still. Arctic ground squirrels let their brains drop below freezing without harm. In the northern tundra, temperatures can fall so low that even the air itself crackles. The Arctic ground squirrel survives it by letting its body become colder than ice. Deep underground, it curls into a ball, its core temperature falling several degrees below zero. Remarkably, ice never forms inside its cells. Special proteins protect. Membranes and high concentrations of glucose act as cryoprotectants. During this time, its brain shows no measurable electrical activity. Its heart slows to almost nothing. And yet, it remains alive. Several times each winter, it briefly warms itself back to normal, then slips again into its frozen trance. This rhythm of freeze and thaw prevents cellular stress from building up and keeps the body ready for revival. Scientists study this creature as a living key to medical cryopreservation, because it demonstrates that the boundary between frozen and alive is not as absolute as once believed. Painted turtles survive winter without taking a breath. In frozen ponds across North America, painted turtles sleep buried in mud for months under thick ice. Oxygen cannot reach them, yet they remain alive. Their metabolism slows to such an extent that breathing becomes unnecessary. Instead, they rely on chemical reactions that produce energy without oxygen. These reactions generate acid, which would normally destroy tissue, but the turtle shell absorbs it like a sponge. Calcium compounds within the shell neutralize the acid, keeping the blood balanced. Heartbeats slow to once or twice each minute, and nerve activity almost stops. When the thaw arrives, oxygen returns, and the turtles revive within hours, perfectly unharmed. Their biology offers clues for protecting human tissues when blood flow is interrupted. They prove that life can endure without breath, not through magic, but through quiet chemistry, affected by millions of winters. Scientists are studying torpor to help protect astronauts in deep space. Spaceflight is one of humanity's most extreme frontiers, but the human body is not built for it. Long missions require food, oxygen, and protection from radiation. Hibernation could solve all three. By studying animals that enter torpor, researchers are learning how to safely slow human metabolism. In theory, a person in torpor would need only minimal resources and would be less vulnerable to radiation damage because slower cells suffer fewer mutations. Experiments with mammals have already shown that induced hibernation can be triggered with cooling and targeted brain stimulation. NASA's exploring this idea for future missions to Mars and beyond, imagining crews that rest for months while machines handle the journey. The body would be cooled, heart rate slowed, and oxygen use minimized, just like a hibernating animal. It is a vision where the science of survival on Earth could one day carry us through the stars. Hibernation shuts down immunity and restarts it without harm. Most living things depend on constant immune defense, but hibernators switch theirs off entirely and somehow restart it flawlessly. As temperature drops, white blood cells vanish from circulation, retreating into organs where they remain dormant. Inflammation stops. The immune system becomes almost silent, conserving energy while food is scarce. When spring warmth arrives, it restarts perfectly without confusion or overreaction. There's no lingering inflammation, no infection waiting in ambush. The process functions like a clean reboot of the body's defense network. Researchers believe that this precise control could transform human medicine, especially in organ transplants or autoimmune diseases. Understanding how hibernators pause and reset immunity may teach us how to rest the human immune system without harm, offering new ways to heal by mimicking the calm intelligence of winter itself. Dormice sleep through more than half the year in hidden burrows. For dormice, the year is divided sharply between abundance and absence. During the warm months, they feed tirelessly, building fat reserves that will sustain them for the long sleep to come. As the air cools, they curl into nests lined with moss and leaves deep underground. Heart rate falls, breathing nearly stops, and their temperature matches the surrounding soil. They can remain like this for 6 months or longer, waking only when the scent of spring reaches the surface. The name dormouse itself comes from the Latin word for sleep, a fitting title. for a creature whose life depends on perfect timing. They sleep through winter storms, predators, and hunger, trusting that patience will preserve them. When they emerge, they are not weakened, only ready. Their secret is simple. They survive not by fighting the seasons, but by flowing with them. Hummingbirds enter nightly torpor to survive the chill. When twilight cools the air, a hummingbird faces a brutal math problem. Its engine runs so hot that a few cold hours could drain every calorie it gathered that day. The solution is torpor, a controlled shutdown that can drop body temperature by more than 20 degrees and cut energy use to a tiny fraction. Perched on a twig, it loosens its grip into a locking tendon, so it will not fall, folds its feathers tight to limit heat loss, and lets the world go dim. Heartbeats that roared during flight slow to a gentle pulse, and breathing settles into long, quiet intervals. Just before dawn, a tiny furnace of brown fat ignites along the shoulders and neck, warming blood that rushes to the brain and muscles. Within minutes, the bird lifts off, bright as a spark. Each night is a narrow escape, solved by precision rather than size. Hibernators lose almost no muscle despite total immobility. A season without movement should waste tissue, yet true hibernators hold their strength as if time barely passed. Deep inside, protein recycling is rewritten. Instead of discarding nitrogen and urea, the body reclaims it to build new amino acids. Muscle fibers retain their structure because enzymes that break protein are dialed down, while enzymes that rebuild are kept humming at a baseline. Nerves maintain their connections, and periodic micro-shivers keep blood and nutrients flowing without spending much fuel. Even mitochondria adapt, shifting toward efficiency that preserves fibers under low oxygen and low temperature. Studies in ground squirrels and bears show intact cross-sectional area and contractile power after months of stillness. The insight is powerful. Weakness after bed rest is not inevitable. Biology already contains a blueprint for preserving tissue through long pauses. A plan written in careful balances rather than brute activity. Desert toads sleep underground for years waiting for rain. In landscapes where seasons are defined by thirst, survival depends on patience. Spadefoot and other desert toads burrow deep when the soil begins to crack. They shed layers of skin into a waterproof envelope, slow their heartbeat to a whisper, and rely on fat reserves. Measured not in days but in years, their bodies conserve water so completely that they can endure droughts that erase ponds and harden rivers. They listen for low-frequency rumbles that signal distant storms. When thunder finally touches the ground above, they wake quickly, climb into floodlit puddles, and call in choruses that can fill a new pond with eggs in a single night. Tadpoles race through development before the sun can erase their nurseries. This is hibernation tuned to dryness rather than cold, proof that torpor is not a winter story but a survival language that deserts teach fluently. Brain activity nearly vanishes, yet remains able to sense danger. During torpor, the brain retreats to a minimal mode that saves energy while guarding the gates. Large-scale rhythms shrink, synapses temporarily disconnect, and neurotransmitters drop to quiet levels. Yet specific circuits stay responsive to critical cues like the smell of a predator, a rise in carbon dioxide, or a sudden vibration. This selective vigilance keeps an animal safe without paying the full cost of wakefulness. When a threat appears, a cascade restores temperature and blood flow to essential regions first, bringing awareness back in a controlled sequence. Memory survives because synapses are protected by special proteins that stabilize them during the cold phase, then guide reconnection during the warm phase. The result is remarkable. A brain can dim almost to darkness, but it leaves a pilot light burning, ready to relight perception in seconds if the world demands it. Bumblebee queens hibernate alone beneath the soil or winter after summer colonies collapse. A single newly mated queen becomes the entire future of the hive. She digs into cool earth, curls her legs beneath her, and lets her body slip into deep torpor. Stored sugars and fats ration out slowly. Her spiracles close tightly to conserve moisture, and her muscles remain ready for the first warm day. Frost passes through the soil above her, and predators move overhead. But she holds still. When spring arrives, she climbs into weak sunlight and immediately scouts for a nest site, often a small hole left by a mouse. She forages alone, warms her flight muscles with buzzing heat, and lays the first brood that will become workers. From that lonely winter sleep, an entire city of bees rises. The strategy is risky, but it allows the species to bridge the gap between seasons with a single living thread. Bears give birth during hibernation without ever waking fully, deep in the den, while snow seals the entrance. A pregnant bear shifts from energy conservation to a precise developmental schedule. Her cubs arrive tiny and nearly hairless, each the size of a small fruit. She remains in a torpid state, yet the nerves that control nursing and maternal responses are fully active. Milk production begins. Without the normal demands of high food intake because her body routes stored fat into rich calories, the den stays warm enough from her metabolism and the insulation of bedding to keep the cubs safe. For weeks they nurse and grow, while she barely moves. When the den opens, the infants are transformed, now strong enough to cling and follow. This pairing of dormancy with reproduction is a masterclass in budgeted energy. The mother spends almost nothing on movement but everything on growth, and the result is new life carried through winter on a quiet tide. Artificial torpor may reduce radiation damage during space travel. Radiation is a constant hazard beyond Earth's magnetic shield. Fast-moving particles can slice through tissues and disrupt DNA. One promising idea is to slow the body so that vulnerable processes happen less often and repair systems have more time to work. In laboratory studies, induced torpor has been linked to reduced oxidative stress and calmer inflammatory responses, both of which can amplify radiation harm when uncontrolled. Cooling the body and lowering metabolism could also shrink the size of life support systems, freeing mass for shielding where it matters most. Engineers imagine habitats that guide crews through safe cycles of torpor and waking checks, aligning sleep periods with solar storms when activity is most dangerous. The path from animal models to human protocols will require careful steps, but the concept is elegant. Survival in space might begin with learning to be still at the right moments. Some animals stockpile fat that can produce heat directly. Not all fat is merely storage. Brown adipose tissue is a specialized heater packed with mitochondria and a protein that allows energy to be released as warmth rather than captured as chemical fuel. Hibernators build and position this tissue with precision around the spine, neck, and shoulders where warm blood can quickly reach the heart and brain during arousal. When a sleeping body needs to wake, hormones ignite brown fat, flooding nearby vessels with heat that spreads through the core. This system works without shivering and without the high oxygen demands of muscle contractions, an advantage when air is scarce and time is short. Infants of many mammals carry brown fat for the same reason, bridging the vulnerable hours after birth. The design is simple and brilliant. Store energy as white fat for the long haul, and keep a separate furnace of brown fat for the instant spark. Evolution invented hibernation many times across unrelated species, from frogs and ground squirrels to insects and fish. Dormancy strategies appear on distant branches of the tree of life. That repeated emergence suggests powerful advantages whenever environments swing between feast and famine. In each lineage, evolution solves the same core problems with different tools. Amphibians lean on sugar-based cryoproction. Mammals refine hormonal control and protein recycling. Insects orchestrate diapause by pausing development altogether. The common thread is the ability to reduce demand when supply vanishes, then restart in a controlled way when conditions improve. This convergence is a map of nature's priorities. It shows that selection can favor patience as strongly as it favors speed, and that pausing life's processes can be as sophisticated as accelerating them. Hibernation is not a single trick. It is a family of solutions that keeps reappearing wherever climate cycles set the rules. Lemurs in Madagascar are the only primates that truly hibernate. High in the spiny forests of Madagascar, fat-tailed dwarf lemurs prepare for the dry season, not with migration or stored food, but with deep hibernation. They gorge on fruit until their tails swell with fat reserves, then retreat into hollow trees. Inside, their heart rate slows from more than 100 beats per minute to barely 6, and breathing may pause for minutes at a time. Their body temperature drifts with the air, sometimes dropping close to ambient. For as long as 7 months, they remain hidden, surviving entirely on stored energy. Every few days, they stir briefly to adjust position before falling back into stillness. No other primate on Earth does this. The discovery reshaped what scientists believed about the limits of mammalian adaptation, and even suggested that the ancestors of humans might once have held a similar ability. It is a reminder that deep rest and complex consciousness need not be opposites. Hibernation suppresses pain signals throughout the body. When an animal enters torpor, the same cold that slows its heartbeat also changes how nerves carry information. Pain receptors become less responsive, and signals that would normally trigger discomfort are muted or never reach the brain. Experiments with hibernating ground squirrels show that even severe injuries cause little or no immediate reaction during the deep phase. Chemicals that drive inflammation are also reduced, keeping swelling and tissue damage low. This suppression helps the body conserve energy and avoid wasting resources on sensations that would serve no purpose while immobile. It also allows healing to proceed quietly in the background. For medicine, this natural anesthesia holds enormous promise. If humans could mimic hibernation's control of pain without losing consciousness, surgery and trauma care could be revolutionized. The idea that cold silence might carry its own form of relief gives new meaning to the phrase rest and recover. Garter. Snakes crowd together in huge underground dens for warmth. In the frozen north, garter snakes face winters too harsh for solitary survival. Their solution is community. As temperatures fall, hundreds or even thousands of snakes slither into ancient limestone cracks and burrows that extend deep, enough to stay above freezing. They coil tightly in layers, their bodies touching, their heat pulled in a shared pocket of air. The den breathes slowly through narrow openings, keeping oxygen levels just sufficient for survival. Each snake lowers its metabolism until a single breath may last minutes. For months, they remain in this living braid, conserving what little warmth the earth offers. When spring sunlight penetrates the stones, the mass begins to stir, scales rubbing softly together in a sound like rustling leaves, the emerging waves spreading across fields and ponds to feed and mate. It is an extraordinary display of cooperation in creatures often imagined as solitary, a testament to how even cold-blooded lives depend on connection. Certain enzymes only function at near freezing temperatures. Some animals and microbes that thrive in cold environments carry a molecular toolkit built for chill. Bare enzymes, the biological machines that drive chemical reactions, work best when most others would grind to a halt. In these cyclic organisms, the enzymes are unusually flexible, allowing them to move and bind molecules despite the thickened consistency of trolled cytoplasm. This comes at a cost. At higher temperatures, they can unfold and fail. Yet in ice and permafrost, they are perfect. Fish, for instance, produce cold active enzymes that keep digestion running even when seawater dips below zero, while Arctic bacteria use similar chemistry to recycle nutrients trapped in frozen soils. Studying these proteins has revealed new ways to design industrial processes that operate without heat, saving energy and reducing waste. Life, it turns out, does not merely endure cold. It can tailor its very machinery to thrive in it. Painted turtles switch to anaerobic metabolism when trapped under ice. When winter locks ponds beneath a solid sheet of ice, painted turtles settle into the muddy bottom, unable to surface for air. Instead of suffocating, they switch to a backup system. Their metabolism slows until energy use is minimal and cells draw power without oxygen, relying on stored sugars. This anaerobic state produces lactic acid, which would be deadly if it built up unchecked. The turtle skeleton solves that problem by absorbing acid and releasing calcium carbonate to neutralize it. Their shells literally act as chemical buffers that keep blood chemistry stable for months. When spring sunlight melts the ice, the turtles awaken slowly, resume breathing, and expel the excess acid as carbon dioxide. It is one of the most astonishing adaptations in vertebrates, proof that survival can depend on chemistry as much as endurance, and that even a shell can serve as both armor and life support system. The pineal gland tells animals when to begin their winter rest. Deep in the brain, the pineal gland reads the language of light. As days grow shorter, it releases melatonin in longer nightly bursts, signaling that the season is shifting. This hormone acts like a calendar for the body, coordinating the cascade of changes that lead to hibernation, slower metabolism, altered appetite, and the conversion of white fat into the brown kind that dabbily generates heat. In some species, The pineal gland even communicates with genes that adjust circadian rhythm, rewiring daily cycles into seasonal ones if the light pattern changes suddenly, such as from artificial illumination. Hibernation may be delayed or disrupted. This sensitivity links the ancient biology of survival to the simplest rhythm on Earth, day and night. Every flicker of dawn and dusk is a message, and the pineal gland is its translator, whispering to the body that it is time to sleep, to wake, or to wait a little longer. Long sleepers tend to live longer because of reduced metabolic stress. In animals that hibernate or enter torpor regularly, there is growing evidence that longevity follows. Each pause reduces the total wear inflicted by constant metabolism. During torpor, oxygen demand falls, free radicals decline, and enzymes that repair DNA have more time to work unopposed. Organs that would otherwise age through continuous operation rest like machines shut down between shifts. Even telomeres, the fragile caps at the ends of chromosomes, seem to erode more slowly in species that experience seasonal dormancy. When compared with their active relatives, hibernators often live years longer despite similar body size and diet. The lesson reaches beyond biology. Slowing down extends not just life but quality of function. Time does not only pass through movement, it also gathers in moments of stillness. Nature's longest-lived creatures may owe their years not to strength, but to the art of measured silence. Fossil burrows suggest some ancient reptiles hibernated underground in the rock layers of the Karoo Basin and other fossil-rich regions. Paleontologists have discovered coiled skeletons inside preserved tunnels. These ancient burrows date back more than 200 million years, and the postures of the occupants, tucked limbs, curled tails, and resting heads suggest dormancy. Traces of soil chemistry and microscopic features confirm that these reptiles sealed themselves in during harsh droughts or cold seasons, waiting for better conditions. Their modern descendants, like certain lizards and crocodilians, still use similar strategies, hinting that hibernation-like behavior has deep evolutionary roots. These fossils expand the story of torpor far beyond mammals, showing that even in the Triassic world, when dinosaurs were just beginning to emerge, some creatures had already mastered the secret of sleeping through hardship. Hibernation is not a new invention. It is an ancient rhythm older than mammals, older than flowering plants, and written into the bones of time itself. Cryogenic sleep might one day carry humans between the stars. For now, the idea lives in science fiction, but every discovery about torpor brings it closer to reality. If metabolism could be safely slowed for weeks, months, or even years, interplanetary voyages could be undertaken without vast stores of food or constant life support. Medical researchers have already induced short hibernation-like states in rodents and observed protective effects against injury. The challenge lies in scaling that precision to humans without damaging organs or cognition. Space agencies imagine cryosleep pods that lower temperature and metabolic rate under careful control with automated systems that periodically wake crew members for monitoring. Beyond exploration, the same technology could transform medicine on Earth, allowing patients to be stabilized for transport or stored between procedures. It would make the boundary between sleep and survival blur into something entirely new. A pause long enough to cross the gulf between worlds. Every spring brings billions of awakenings hidden from sight. When the four begins, an entire planet exhales. Beneath melting snow, frogs stir from their icy tombs. Insects crack open soil chambers and mammals rouse from den to the thin light of dawn. Microbes reawaken in wet earth, restarting the chemistry that will feed roots and leaves. Rivers swell, carrying nutrients, released by decomposition, and the first shoots of green answer the call. This mass awakening is not a single event, but a wave that travels north with the warming sun, reanimating ecosystems in sequence. By midsummer, the pulse of life reaches the Arctic, completing a circuit that began months earlier near the equator. For every heartbeat that slowed in winter, another now returns. The scale is almost impossible to imagine. Billions of tiny revivals, adding up to one planetary rhythm. Hibernation does not end with a single animal's yawn. It ends with the Earth itself taking a breath. Hedgehogs cool their bodies until they almost match the air around them. As the light fades from autumn fields, hedgehogs vanish beneath drifts of leaves and moss. They curl into perfect balls, noses tucked against bellies, spines pressed outward like armor. Inside their nests, the temperature slowly falls until their bodies cool to nearly match the air around them. Heartbeats that once raced at hundreds per minute drop to only a few. Breathing becomes faint and rare, a quiet pulse of life that barely disturbs the air. Fat stores sustain them for months as their internal chemistry turns minimalist, burning just enough fuel to keep cells alive. On warm nights, they sometimes wake, shift position, or rebuild the nest, then return to their trance of cold calm. By the time spring sunlight melts the frost, the small bodies stir, hearts quicken, and their sleepy eyes blink open. They step out as if the long winter never truly happened. Hibernating. Mammals recycle waste to nourish their own tissues. Inside a hibernating body, almost nothing is wasted. Fat provides energy. But the real miracle lies in how these animals handle nitrogen waste. In ordinary life, urea is excreted through urine, carrying nitrogen away. During hibernation, this would be lethal dehydration. Instead, the body reuses it. Specialized microbes in the gut break urea apart and feed its nitrogen back into the bloodstream, where it is used to build new proteins and repair tissues. Muscles remain strong, organs stay intact, and nothing toxic accumulates. Even the gut bacteria change roles to help recycle. Instead of digest, when the sleep awakes, the system resets smoothly. Kidneys clear the final traces, and the animal steps out of its den in almost perfect balance. It has eaten nothing, yet lost little more than fat. The process is a natural model of efficiency that engineers and doctors still struggle to match. Bears maintain bone strength, despite total inactivity. A bear can lie motionless for half a year, yet when it wakes, it stands on legs that are still strong. While human bones weaken rapidly in bed rest or spaceflight, bears preserve theirs through supple control. The cells that dissolve bones slow almost to a stop, while those that rebuild continue at a gentle pace, maintaining perfect balance. Calcium moves in a closed loop between blood and bone, never lost. The marrow still produces new blood cells, and hormones adjust to keep minerals circulating without waste. Scientists believe this adaptation could one day help prevent osteoporosis in people confined to long recovery or weightlessness. To the bear, it is just survival. In silence and darkness, its body keeps renovating itself. The den hides not decay but maintenance, a kind of slow construction that carries strength through the stillness of winter. Time perception shifts as metabolism slows almost to zero. In deep torpor, time itself bends. Brain cells fire so rarely that seconds stretch, and the usual rhythm of experience dissolves. A day might pass with only a handful of heartbeats and a few shallow breaths. The brain's internal clocks drift into near stasis, and the dividing line between sleep and death becomes razor thin, yet awareness is not erased, only muted. When the animal wakes, it senses the world as if from a long blink. For it, the dark months are not endured but skipped, folded into a single moment of stillness. Some researchers call it the closest natural form of suspended consciousness. Others see it as proof that biology can edit time, slowing it until life passes, almost unseen. The world outside changes completely, but for the sleeper, the interval between falling asleep and waking again is a single heartbeat. Microbes in permafrost can awaken after thousands of frozen years. Deep within ancient Arctic soil, microbes lie locked in permafrost older than civilization. Yet, when thawed carefully in laboratories, many of them awaken. They move, feed, and divide as if no time has passed at all. Their survival rests on biochemical tricks that protect DNA and proteins from freezing damage, and enzymes that repair molecules fractured by radiation and ice. Some have been revived from ice more than 30,000 years old. Their reawakening has changed how scientists think about life's endurance. It proves that metabolism can pause not for seasons but for ages, waiting patiently for a return of warmth. If Earth can harbor living cells through millennia of ice, perhaps frozen moons and planets might do the same. In each drop of thawed permafrost lies a whisper from deep time, reminding us that life's truest strength is its refusal to vanish. Hibernation triggers a complete shift in Blood chemistry. Before an animal slips into torpor, its blood begins to change. Sugars rise to protect cells from cold, salt levels adjust, and the balance of proteins shifts to prevent clotting or dehydration. Oxygen binds differently to hemoglobin, ensuring that even at a faint pulse, tissues still receive enough to survive. Fatty acids reorganize, so that blood remains fluid when chilled, and the immune system quiets to avoid wasting energy. The result is a bloodstream, redesigned for neostasis, a liquid environment that keeps organs alive at a fraction of normal function. When warmth returns, the chemistry reverses in precise order. The blood becomes active again. Coding resumes and the heartbeat accelerates without shock. To call it adaptation is too simple. It is metamorphosis within a single body, a transformation so smooth it can repeat for decades without error. Frozen flood their cells with sugar to stop ice from tearing tissue. As winter closes in, certain frogs perform one of nature's most astonishing feats. Their hearts stop beating, their lungs stop breathing, and ice forms inside their bodies. Yet they do not die before freezing. Their livers release massive amounts of glucose and urea into the bloodstream. These chemicals act as antifreeze, pulling water out of vital cells and preventing sharp crystals from forming inside. Ice forms only in safe spaces, between cells. For weeks or months, they remain frozen solid, their metabolism halted. When spring light warms the forest floor, the ice melts, the sugar thins, and their hearts begin to beat again. Within hours, the frogs hop away, as if nothing happened. Their survival has inspired research into organ preservation and cryonics, but no human technology has yet equaled the precision of a frog that can die, thaw, and live. Again, controlled torpor could revolutionize emergency care. When blood flow stops, during trauma or cardiac arrest, cells begin to die within minutes. Hibernators point to another way. By slowing metabolism, reducing temperature, and cutting oxygen use, life can pause long enough for rescue. Scientists are testing ways to induce this torpor in humans through gentle cooling and chemical triggers that mimic natural signals. In trials with animals, the technique has protected brains and hearts through severe oxygen loss, buying precious time for recovery. Doctors imagine emergency rooms where critical patients are cooled within minutes, preserved in metabolic silence while damage is repaired. The idea once belonged to science fiction, but nature has proved it works. If it can be mastered safely, controlled torpor could change the limits of medicine itself, giving humans the same power that lets a ground squirrel sleep through an entire season unharmed. Group torpor can spread through colonies like a shared rhythm. In a winter cave filled with bats, sleep becomes contagious. As one individual slows its heartbeat and breath, the temperature drop ripples through the cluster. Soon hundreds hang, motionless together, their combined body heat forming a pocket of air just warm enough to prevent freezing. Each tiny heart echoes the next, and the group falls into a collective rhythm that holds through the long, cold months. This synchronization conserves energy far better than solitude could. When the first warm currents of spring drift into the cave, the change passes through them. Again, one stirs, then another. And soon, the whole colony wakes in waves, stretching wings and shaking frost. Group torpor is more than a coincidence. It is a social version of hibernation. Proof that even in stillness, life can move together in unison. Nature rests, waits, and renews through this ancient cycle of pause. Every year the planet exhales, rivers slow, forests fall quiet, and animals disappear into secret refuge. What seems like death is preparation. Beneath snow and soil, the machinery of renewal hums softly. Nutrients settle, roots mend, and water gathers underground. The air clears, ecosystems reset, and balance returns then. As the tilt of the earth brings back the sun, the silence ends, frozen ponds stir, soil warms, and an explosion of green and song follows. Hibernation is not an interruption of life, but part of its heartbeat, a universal rhythm that keeps chaos from burning the world out too quickly. Rest, wait, rise, repeat. The cycle is ancient and precise. The reason spring feels like resurrection instead of mere routine. Stillness is not the opposite of life. It is how life gathers strength to begin again. Echidnas drift in and out of torpor through the Australian winter. In the Rocky Hills and eucalyptus forests of southern Australia, echidnas survive the cold season through a rhythm that is neither full wakefulness nor true hibernation. They slip in and out of torpor, adjusting to the shifting weather. When the air turns icy, their body temperature falls close to the ground's and their hearts slow until the pause between beats lasts many seconds. When sunlight returns for a few days, they stir, forage for ants, and then sink back into stillness as the chill deepens. Again, this pattern can last for months, creating a slow alternation between activity and rest that saves enormous energy while keeping them alert to opportunity. Sometimes males even wake briefly to mate during warm spells before returning to sleep. The echidna's flexible cycle shows that survival does not always mean full surrender to the season, but can be a dance between movement and pause. Hibernators age more slowly than active animals of the same species. When the body's engine slows, time itself seems to hesitate. Hibernation reduces the stress that daily metabolism places on cells. Oxygen demand drops, harmful free radicals decline, and DNA repair systems have time to restore microscopic damage that accumulates with normal activity. Over a lifetime, this means fewer broken molecules, fewer errors, and longer preservation of function. Ground squirrels, bats, and other hibernators live noticeably longer than related species that remain active all year. Even their mitochondria, the power plants of cells, produce less waste heat and fewer damaging byproducts. Telomeres at the ends of chromosomes erode more slowly, delaying the biological clock of aging. The effect is not magic, only balance. Life extended by restraint. To sleep, through hardship, is to step outside the wear of constant effort, proving that sometimes the best way to preserve life is to live more slowly. Parasites within hosts can also enter torpor until conditions improve. Even the smallest dependents of hibernating animals follow the same rhythm of stillness. When a ground squirrel, bat, or bear enters torpor, its internal companions, from worms to microscopic protozoa, reduce their activity too. They slow reproduction, halt feeding, and wait for warmth and nutrients to return. If they did not, their hunger could harm or kill the host before spring arrived, destroying their own future in the process. Some parasites produce protective coatings that let them survive the chill, while others rely on the host's lowered body temperature to trigger their own suspended state. When the animal wakes, circulation restarts and the parasites stir with it, resuming the ancient cycle of coexistence. It is an uneasy partnership, but an enduring one, shaped by shared dependence on patience. Even life that lives upon life knows when it is wiser to wait. Heart rhythm changes shape to cope with slower beats. When an animal's heart slows to a few beats each minute, it must completely reorganize its pattern to survive. In hibernators, electrical impulses stretch apart and the muscle fibers contract in long, deliberate waves. Each heartbeat pumps more blood per stroke, compensating for the slower rhythm. Ion channels in the heart cells shift to favor stability over speed, keeping each contraction smooth and reliable. Blood becomes slightly thicker, allowing it to flow gently without pooling or clotting. In some species, the shape of the heartbeat itself changes when measured on a monitor, flattening into soft curves that echo the stillness of sleep. When warmth returns, these same hearts accelerate effortlessly, resuming the fast tempo of active life. The transition is seamless. A system designed for movement learns how to rest, proving that even the heart can become fluent in quiet. Arctic fish make natural antifreeze to survive sub-zero seas. In the polar oceans, temperatures drop well below the freezing point of pure water. Yet fish swim calmly through it. Their blood carries special proteins that attach to the smallest ice crystals and stop them from growing. This prevents freezing, even when seawater turns to slush around them. These antifreeze proteins are an evolutionary masterpiece fine-tuned over millions of years to work precisely at the edge of danger. The fish can hunt and reproduce in water that would kill most other species within minutes. Scientists have used similar molecules to protect frozen foods, preserve tissues, and even improve frost resistance in crops. But no artificial version matches the natural balance found in these fish whose veins carry liquid life through liquid ice. In a world built from cold, they have rewritten the chemistry of survival. Hibernation research may unlock the secret of suspended animation. Every discovery about hibernation brings science closer to understanding how to pause life safely. In laboratories, researchers have cooled small mammals and triggered deep torpor using specific gas mixtures and metabolic signals. Animals awaken later unharmed, their organs preserved, their minds intact. The implications are vast. If humans could one day enter a controlled torpor, it could revolutionize medicine, allowing trauma patients to be stabilized for long transport, or giving surgeons time to work with near-perfect precision. Astronauts might travel between planets, while using only a fraction of the food and oxygen they would need awake. The challenge lies in restarting the body, gently warming tissues in exact sequence so that chemistry remains balanced. Nature has solved this problem countless times. We are only beginning to understand how some species wake briefly to eat cached food mid-inter. Not every hibernator sleeps straight through the season. Chipmunks and certain mice live by a schedule of short, deliberate awakenings. Before winter, they store seeds, berries, and nuts in intricate chambers beneath the soil. When their bodies cool and slow, they sleep for days or weeks, then rise just long enough to eat and drink. These brief returns to wakefulness restore energy reserves and prevent starvation if conditions last longer than expected. They also help the animals check their hoards and remove mold or decay that could poison future meals. Each awakening is short, efficient, and essential. This pattern balances deep rest with vigilance, a careful compromise between torpor and alertness. Through this rhythm, the animals endure long winters that would otherwise drain them completely, proving that sleep can be strategic as well as restorative. Deep torpor suppresses cancer cell growth in some studies. In the stillness of hibernation, every process slows, including the harmful ones. Experiments on hibernating mammals show that tumors stop growing when metabolism merely halts. Cancer cells deprived of energy and oxygen fail to divide, while normal cells enter a protected state that resists damage. In laboratory models, researchers have replicated these conditions by cooling animals or using chemical signals that mimic torpor. The results are striking: reduced inflammation, slower tumor progression, and fewer mutations. The cold seems to give the body time to repair itself without interference. If these mechanisms can be adapted to human medicine, doctors may one day place patients into controlled torpor to halt disease temporarily. It is a bold vision, yet it mirrors what nature already proves each winter, that rest can be the most powerful form of defense. The scent of spring soil can trigger awakening. For animals buried beneath the ground, the first hint of spring is not sight or sound but smell. As the frost softens, microbes awaken and release faint chemical signatures that drift through the soil. Hibernators sense these invisible changes through delicate receptors tuned to trace gases and organic compounds. The signal travels through the brain to the pineal gland, where it alters hormone levels and prepares the body for reawakening. The shift begins gradually. Heart rate rises, blood warms, and muscles regain tone. When the animal finally emerges, it is responding not to temperature alone, but to the scent of life returning. The fragrance of Ford earth, rich and subtle, serves as nature's quiet alarm clock, reminding every sleeper that the world above is ready again. Hibernation teaches that survival can mean stillness, not struggle. Every winter, millions of animals practice a lesson that life often forgets. Strength is not always motion. In the silence of hibernation, they conserve energy, slow their hearts, and wait for the world to heal itself around them. Their restraint maintains balance in ecosystems that depend on cycles of rest and renewal. When they wake, food and light have returned, and the landscape is ready for growth. Humans, too, might learn from this patience. To endure does not always mean to push harder. Sometimes survival is about trust, about holding still through hardship until the right moment to rise. The world continues while they sleep, yet their stillness shapes its rhythm. Hibernation is not escape, but harmony, a reminder that in the great design of life, even waiting has purpose. The poor is the only bird known to hibernate for months. High among the sun-bleached cliffs of North America, the common pewil performs a feat no other bird can match. When insects vanish and nights grow cold, it settles into rock crevices and lets its body cool until it nearly matches the surrounding air. Its heart slows to just a few beats a minute and breathing almost stops. For weeks or even months it remains still, wings folded tight, feathers dusted with sand. When warmth returns, it wakes slowly, stretches its wings, and glides back into the dawn to hunt. Once again, early naturists once thought these birds had vanished during winter, but careful observation revealed that they had simply chosen to pause. Their discovery transformed what we knew about avian endurance. The pole will's deep rest shows that flight and stillness can belong to the same creature, and that even a heart built for motion knows when to wait. Hibernation allows months of fasting without malnutrition. Most animals waste away without food, yet hibernators bypass this rule completely. Their bodies shift into a chemical state where every resource is recycled. Fat becomes the main fuel, but protein, vitamins, and minerals are conserved with extraordinary precision. Nitrogen that would normally be lost in waste is reclaimed and transformed into fresh amino acids. This closed loop system prevents the muscle and organ damage that fasting usually causes. Bears, ground squirrels, and bats emerge from hibernation lean but strong, their tissues intact, and their immune systems ready. Their metabolism acts like a perfectly balanced budget, spending nothing it cannot replace. Scientists study these mechanisms to understand how humans might one day preserve muscle and organ health during long hospital stays or space missions. Hibernation is not starvation, but mastery of energy itself, a seasonal suspension that proves survival is as much about management as endurance. Amphibians thaw gradually to avoid shock. When the ice melts, when spring sunlight begins to reach the frozen ponds where frogs and salamanders have slept, their revival must unfold slowly. If they thawed too quickly, water rushing back into their cells could cause fatal ruptures. Instead, they wake through a delicate process controlled by chemistry. Sugars and alcohols stored in their tissues during freezing act as natural antifreeze and stabilizes. As the ice around them softens, blood flow resumes in a slow wave, carrying warmth to vital organs. First, the heart beats unevenly at first, then finds its rhythm, and breathing begins again. Within hours, the once rigid bodies flex and push through slush toward the surface. The precision of this sequence allows survival after conditions that would destroy most living things. Each amphibian's awakening is a carefully tuned performance between cold and life, the conclusion of a frozen sleep that bends but never breaks biology. The gut microbiome transforms entirely while the host sleeps inside the hibernator's body. Even the smallest ecosystems adapt to the season of silence. Gut bacteria that thrive on constant meals of plant matter cannot survive months without food. So, they're replaced by species that feed on mucus and internal secretions. This altered community produces fewer digestive acids, but more compounds that prevent infection and maintain intestinal health. When spring returns, the balance shifts again. Food triggers the rebirth of microbes, suited for digestion, rebuilding the internal landscape within days. This partnership between host and microbiome ensures survival for both sides. Without the microbial adjustment, digestion could collapse when feeding resumes. In recent years, scientists have begun to see how profoundly hibernation reshapes the invisible world within. The gut does not merely sleep. It reorganizes itself completely. A miniature season that mirrors the great pores occurring in the rest of the body. Antarctic midgets use sugars to keep their bodies from freezing. The Antarctic midge is smaller than a grain of rice, yet endures one of the harshest climates on Earth. To survive, it replaces much of its body water with a concentrated syrup of sugars and alcohols that prevent ice from forming inside its cells. This mixture acts like biological antifreeze, lowering the freezing point and preserving cell membranes. For most of the year, the midge remains frozen solid within the soil, immobile but alive. When summer sunlight returns, the sugar concentration drops, water flows back, and movement resumes. Their survival depends entirely on timing. A few hours of unexpected warmth or cold at the wrong moment could destroy them. Despite their size, these insects demonstrate one of nature's most elegant survival strategies. They show that complex chemistry, not sheer strength, allows life to persist at the edge of absolute cold. Bears rouse gently every few weeks to stretch and adjust position. Deep in the den, hibernation is not pure stillness. Even when buried in snow, a bear stirs every few weeks. Its body temperature rises slightly, muscles flex, and the animal shifts position to improve circulation and prevent pressure injuries.